Alright, here we go. It's time for Phys111 pre-midterm stuff. Hello. So, if you have questions, you could write them down in the live chat. I don't know if anybody's watching yet. 0 people are watching so far. Well, whatever. So, this particular thing will cover some of the things on the midterm, but it's also going to cover a little bit of stuff past the midterm. Essentially, I'm just covering all the topics we're doing on the assignment, which overruns the midterm by a little bit. Some of the stuff is the calculations we did on Monday. But in other words, all of the questions are below. If you don't know which book to find your questions in, it's the Eric Mazur Black book. It's Principles and Practice of Physics, Volume 1. It's the black book. You dig? There's a white book and a black book. The white book is the one you do pre-reading in. The black book is full of demonstrations of calculations and also the questions from Mastering Physics. So that's where you find either of them. And if you have any questions, let me know. I want to add, a lot of people are nagging me for the answer keys to the practice exams. I did a live solution of the practice exams. The practice exams I gave you were last year's midterms for around this time. We weren't in exactly the same place, so they don't cover the materials in exactly the same way. But it's all on there, and it's all good exercise. And it also gives you a sense of the length and difficulty level of the test. So after we did the midterm last year on one of these online office hour things, I recorded me solving all the questions on it. So if you want to know what the answers are, go watch the video. See if you did it right. So aside from that, we'll be doing these questions on this feed. Also note that one of the practice midterms I gave you doesn't have an answer sheet on it, because one of them was the... Yeah, I don't know where the answers to the third one went. So, I'm sorry. But I'm pretty busy right now, so I don't have time to... This bunny looks terrible. Okay. Without further ado, if you don't have any questions, let's begin. Page 62, question 8. Okay, cart 1 is initially at rest and struck by cart 2, which has twice the inertia of cart 1. Figure 4.8 shows the velocity of cart 2 as a function of time. Complete the graph by adding the velocity of cart 1 during the same time. Okay, so let's get some paper in here. All right, graph paper. It goes up to 8. 1, 2, 3, 4, 5, 6, 7, 8. No. 2, 4, 6, 8. V in meters per second. And T. And cart 2's velocity curve looks like this. It goes the first second 8, and then it goes down to 4 after 2.5. Okay, so that's cart 2. And okay, cart 1 is at rest. So initially it's at rest, so that means initially its velocity is 0. Okay, that's cart 1. struck by cart 2, which has twice the inertia of cart 1. So the change in velocity here is delta v. It's minus 4 meters per second. Cart 2 has twice the inertia, and so delta v of the other one, delta v1, is going to be 2 times delta v2. Its recoil is twice as much because it has half the inertia. So it's going to be minus, there's a minus sign in there. It's going to be plus 8 meters per second. So over the course of this time interval, it goes up to 8 meters per second, like that. I feel like this particular type of calculation is fairly elementary, and I expect you to be able to do it. It's not too tricky. I consider that an easy question. Question 9. Figure 4.9 growth is a position versus time graph for a collision along a straight line between two identical amusement car bumper cars. The inertia of the passengers are different. All right, so in other words, here's one bumper car. It's got like a skinny little kid in it. And the other bumper car, which is the same, it's got like 2 enormous people in it somehow. So they have 2 different inertias, but the inertia difference is because of the people in the car. Which post-collision solid line is a continuation of the dotted line for cart A, which for cart B? Which car contains passengers having greater inertia? Okay. So we gotta be able to talk about what this graph looks like. B, and then A looks like that. And then there's 2 lines coming off it. One that looks like that, and one that looks like that. And the question is, which do these belong to? Which one of these is A, and which one of these is B? So there's a bunch of different ways to think about this, to be quite honest, and they're really fun. So one question here is, let's say, I'm not sure about their inertias, but let's say this one's A and this one's B. No, which one's going faster? B's going faster. So I guess this one's A and this one's B. B's going fast at first because it's got a big slope. A's not going very fast. After the collision, is it possible for B to keep moving faster than A? So right now, B is moving faster than A. Its velocity is more positive than A's is, and so it means it's catching up to him. Is it possible after the collision for this one to still be faster than this one? And the answer is no, because this guy's still in the way. So this, after the collision, this must be moving slower to the right. By slower to the right, I mean that this one's rightward velocity has to be bigger than this one's. So this one must be A, and this one must be B, because they can't pass through each other. Okay, so here's the question. Which car contains the passengers with greater inertia? This is a position and this is time. And we should also note that there aren't any units on the graph in the book, so we can't actually calculate the slope. So which one undergoes a smaller change in slope? I'd say that A's has a bigger change in slope. Absolute value. A's slope changes a lot more. Right now it's pretty shallow and then it gets really steep. Whereas B's is medium and then afterwards it's still kind of medium. So A's velocity changes more than B, so B must have more inertia. Cart B has more inertia. Even though I drew it this way, I guess this little kid is made of solid gold. And yeah, so he's really heavy in spite of the fact that there's not much to him. Next question, let's do it. Question 11. Figure 4.11, oh yeah, look at there, is a velocity versus time graph for two objects before and after they collide. Object B is initially at rest. What factor relates the inertias of object A and B? What factor relates objects A and B? So one thing you might notice if you're trying to do questions out of the book is some of the questions don't really make sense. And that's because they're literal transcriptions of more complicated, more interactive questions on the Mastering Physics system. So it's probably that this question has like some kind of multiple choice. So we want to talk about the inertia of the two. Let me just guess here. It's not going to be the change in velocity of A. And it's not going to be the change in velocity B. It's not going to be either of those. It's not going to be the final velocity or the initial velocity either. Hold on, let me sketch what I'm talking about. You got your A, it looks like that. You got your B, it looks like that. Okay. So V initial A, V initial B, V final A, V final B. This graph is covered in data. Okay. Like, you know that the interaction's happening during this time interval from this time to this time. Before then, they're not touching. It's covered in data. You can tell which one's moving faster, which one's moving slower. But none of these pieces of data on their own tell you anything about the inertia. None of them do. VA doesn't, VB doesn't, VBF, BVI, no. Furthermore, delta VA or delta VB, these guys don't tell you anything about the inertia either. So this one's going to be V final A minus V initial A, V final B minus V initial B. They don't tell you nothing. I mean, it tells you how much recoil the thing had, but you don't know why it's recoiled that much. The inertia can only be gleaned when we compare how much recoil each thing feels. One of these might have recoiled a whole bunch because, if all you knew is this, somebody says, oh, I hit something, and then I had a recoil of, delta V of plus 3 meters per second. That doesn't tell you anything. You might have hit something really lightweight that was moving really fast and who had a much bigger recoil than you, or you might have hit something really heavy that didn't have much recoil. So these two numbers on their own don't tell you anything about the inertia. It's only when we compare them, delta VB or delta VA. It's only when we compare them that we get the ratio of inertias. Incidentally, do you know how to calculate, okay, so when you do this particular relationship, we called it the law of inertia in class. This was really helpful, right? Super helpful equation because, it's like on the first graph here. Somebody gives us delta V1, you have to read it off a graph, M1, M2, and we want delta V2. You're essentially going to use this equation to figure it out. But the problem with this equation is this equation is a bad equation. It's good in that it's true, but it's bad in that it's hard to parse. It's hard to remember. The minus sign in it is fine because otherwise you get a minus thing. If you don't remember the minus sign, that's fine. But how do you remember whether it's delta VA over delta VB is equal to MA over MB, or if it's MB over MA? Which of these two is it? How do you remember? Is it that one or is it that one? And the way to remember it is, this is the law that gives you the conservation of momentum. And momentum is really easy to remember, right? It's MAVA, MBVB. And so when you set up this equation, you just have to remember that it's the one that if you cross multiply, you get the conservation of momentum. So VA and MA are that way, and VA is that way, and that crosses this one out. So it's always switched. That letter's that one, and that letter's that one. So yeah, it's only the ratio of these delta V's that tell you anything about their inertia. I think that's the answer to the question. You know, I choose these questions just by looking at them. I don't do them before we start the video. So the only way I can tell is if what's it called? It occurs to me that I have to restart the QuickTime feed. I'll be right back. Just hold on a second. Okay. So long story short, yeah, that question wasn't very good to answer because I think that's a pure mastering physics question, where it gives you some choices on the mastering physics system. Whoops. So yeah, I don't do the questions before I get here because I want you to see my problem-solving strategies. That's the point of all this exercise. It's when you're sitting down facing a problem, what are you going to do? And then you're going to hear my stupid voice in your head saying all these stupid things, and you're going to say, wow, that's actually pretty smart. Like, I know. I'm good at physics. Okay, question 23. If two cars collide on a low-friction track, it is possible for both carts to slow down. It sure is, yet 4.1 seems to say that because the inertia is always positive, if one velocity increases, the other must decrease. Explain the apparent discrepancy. All right, what's the question? The question says, okay, you got two carts. They run into each other. There's a big velocity. There's a big velocity. And then afterwards, the velocity of the first one is little, and the velocity of the second one is little. And then the question goes, but we thought that the inertia is always positive, and it is, right? MA over MB is always bigger than 0. We thought if one velocity increases, the other must decrease. So minus delta VA over so that number always has to be bigger than 0, right? Which means that if delta VA is positive, delta VB must be negative. Okay, I just got a question from someone named Jeff who says, I got stuck chapter 3, question 45. Chapter 3, question 45. And, hold on. 45 and 53. I'm looking them out right now. 45. 45 and 53. Weird. Okay. I'll add them to the list, okay? So those questions are on page 45, question 43 and 53. Okay. If any of you other have questions, you can always add the questions you want to see me do on the feed. All right, so here was the thing. Both velocities, both slower. This seems to indicate that one has to be increasing in speed and the other decrease in speed. How is it that both can be slower, like this drawing, if one has to increase in speed and one has to decrease in speed? That's the question they're asking you about. And the answer is actually pretty fun. It's because delta V doesn't mean speed up. It doesn't. Delta V is a vector. So if delta V, so for instance, delta V positive, suppose it looks like this, delta V. If V initial is in the same direction as it, we pretty much had the this whole explanation when we were talking about acceleration. If the initial velocity is in the same direction as the acceleration, it corresponds to speeding up. Whereas if the initial velocity is in the opposite direction, V final means that it'll slow down. So one can be positive and one can be negative. That doesn't tell you that one of them is speeding up and one of them slowing down. This is incorrect. Whether or not it speeds up and slows down depends on the initial velocities and a couple other things. But the long and the short of it is, take this example, okay? So maybe VA initial is equal to plus 4 meters per second. VA final is equal to minus 2 meters per second. VB initial is equal to minus 4 meters per second. VB final is equal to plus 2 meters per second. Okay? So essentially I was like, hey, what if the directions look like they are above here, where they are, where one is going to the right and one is going to the left, and then they bounce off each other. In this case, delta V A is going to be final minus 6 meters per second. Delta VB is going to be plus 6 meters per second. Okay, one of these is negative, one of these is positive, just like we posited it up here, but both carts slow down. You went from moving fast to moving slow. Does that make sense to you? Okay. Let's keep on trucking. Boop, boop. Okay. So, what question was that? That was question 23. 49. Let's do question 49. Question 49 goes like this. 3 carts are described in a table collide simultaneously. What's the momentum of the system of 3 carts? Before the collision, after the collision, is the system isolated during the collision according to the data? Oh, fun. Okay. So you got 3 carts. They're heading towards each other, kind of like this. One's running into 2, and then 3's going to rear end 2 at the same time. And so they're going to all bounce off each other. That's the situation. And what we have is a bunch of momentum data. Cart 1, 2, 3, before plus 6, minus 2, minus 3. So it's asking us to do it with the system is all 3 carts. So the total momentum for the system is just these numbers added together. So it's going to be 6, minus 2 is 4, minus 3 is plus 1. After the collision, minus 4, plus 2, plus 3. Add these together, plus 1. These numbers are the same, so the total momentum hasn't changed. So the system is isolated. Is the system and 3 cart isolated during the collision? Yes, it is, because the momentum is the same before and after. Okay. 49, question 50. If you have any questions, ask in the live chat. That's 50. Okay. 2 carts on a low friction track. Cart 1 has initial momentum of 10 kilograms per second and a final momentum of 2, minus 2. If cart 2 has a final momentum of 6, what was its initial momentum? I'm going to talk real slow about this. Okay. Low friction track. Cart 1, I hat direction is that way. Cart 1 is traveling that way. 10 kilogram meters per second. We don't know how fast he's going, but we know it's momentum. Cart 2. Its velocity is a big question mark. Or rather, its momentum is a big question mark. Afterwards, cart 1 is going like that. Minus 2.0 kilogram meters per second. And cart 2, I guess cart 2 is going like this. Okay, so wait, what? Cart 1 has initial momentum of 10. I had minus 2. Oh, okay. Right. Fine. We're cool. We're cool. So this is still cart 1, cart 1. Cart 1 has a final momentum of minus 2 kilogram meters per second. And this is minus 6 kilogram meters per second. This is actually a neat explanation. The thing that was catching me up was way here earlier, blah, blah, blah. Where were we? This one. This question. Remember how I was talking about how they would be arranged so that this guy couldn't actually pass through A? And that tells you their final velocities. How their final velocities have to compare. Well, I was getting caught up in this one because 10 kilogram meters per second going this way seems to indicate, and then going this way seems to indicate that this guy's on the right-hand side of that one. And then when you do it, this is a bigger number than this. And I was like, hey, wait, isn't that wrong? And the answer is that these aren't the velocities, these are the momentum. Velocity plays a part, but the momentum can be big because it's traveling fast, or it can be big because it's got a big inertia. Okay, so what's the final momentum? What's the initial momentum of cart 2? This is what I want to know. To answer this question, I need to figure out whether or not the system is isolated. You can do it a couple different ways. One of them is you can look at this as 2 systems. This one and this one. and talk about whether or not they're exchanging momentum. Alternatively, you could argue that because this is a low friction track and presumably horizontal, this, erase the track. Because it's a low friction track and clearly it's horizontal, this whole system before and after is going to be isolated throughout. So isolated, and that means the total momentum is going to be the same. So initially it's 10 plus P2, and then finally it's going to be minus 2 minus 6 is equal to minus 8. So then we compare, and then we say 10 plus P2 has to equal minus 8, so P2 has to equal minus 18 kilogram meters per second. Okay. All right. Next question. So, long story short, it always pays when you're doing one of these questions to draw it out. Draw the picture. I can't emphasize this enough. Draw the picture. Try to make sense of the question. Because there's a couple reasons. One, you get to waste some time. You get to think about things. But another reason you get to do it is it helps you test to see if you're right. Because sometimes if you just use the equations and you have no idea what you're doing, you have no idea whether or not you've made a mistake. So if you've got a picture and you're thinking about what you expect to do in the calculation, it kind of gives you a sense as to whether or not you're doing it correctly or not. 63. Playing pool, you send the cue ball head on, that is in a line joining the center two balls, into the stationary 8 ball. The cue ball stops as a result of the collision. Describe the momentum of the each ball before and after the collision. So there's the cue ball. And there's the 8 ball. So initially, the cue ball has all the momentum because it's rolling. And this guy stays still. And then after, the cue ball stays still and the 8 ball has all of the initial momentum. Show that your answer for part A is consistent with the idea that the momentum, okay, so where did I get this argument that this momentum is the same as this momentum? I'm given a sense of their velocities based on the description, but why would I argue the momentums are the same? Essentially, over the surface of a pool table, it's fairly horizontal. Objects rolling don't really lose much, don't interact much with the table, so it's not like it's losing energy to the table. We'll get to that later. But long story short, this is an isolated system. And so because it's an isolated system, because I recognize that it's an isolated system, I can argue that these two are the same magnitude. So now it wants us to talk about delta P is equal to J. So let's consider these two systems individually. The red system and the blue system. For the blue system, which is the cue ball, J is the change in momentum. How much momentum is entering or exiting? And you can calculate it. P final minus P initial. So it's minus PQ. For the red one, which is the 8 ball, P final minus P initial. So that's, the final is PQ minus 0 PQ. So I had argued that these two values, this one and this one, these two momentums were the same by arguing that the system composed of the cue ball and the 8 ball was isolated. If I consider each of these pool balls separately as systems, their momentum's going to change. And indeed, the momentum lost by this system is equal to the momentum gained by this system. And I think that's what it wants when it says, show your answer part A is consistent with the change in momentum equal J, I think. At least that's as much sense as I can make out of this weird question. It might be that this question has more parts to it on mastering physics, I don't know. 79. A bullet of inertia M bullet is fired horizontally with a speed V bullet into a stationary wood block of inertia M block lying on a low friction surface. The bullet passes through and emerges with the speed B bullet final. Determine the final speed of the block in terms of the given quantities. So let's draw the picture. You got a bullet and it's traveling with some velocity. V bullet initial. And then you got a wooden block. V wood is equal to 0. M bullet, M wood, and it's on a very smooth surface. So after it passes through, your wood block's going to have a little hole in it. Fine. But presumably it's got the same volume. The bullet has the same volume, but it's traveling at a different speed. And so the question is, what's the velocity of this guy? The trick to doing this is actually related to the previous one. We can make a couple different arguments. So let's consider them as a system together. So the system is the bullet and the wood. Hey, that looks like Disney's signature. Way to go, me. Okay, so we can argue that this system is isolated because it's on a smooth surface. So P total initial is going to be P total final. The initial momentum is MB V block I. The final momentum is going to be M wood V wood final plus M block V block final. And so we want to rearrange and figure out what that guy is. So it's MB VB initial minus MB VB final is equal to M wood V wood final. And so V wood final is equal to MB VB initial minus MB VB final divided by M wood. Oh, somebody asked a question. Please include chapter question 45, 47, and 71 from chapter 3. It's been days and I still don't have the right approach to them. Okay, 45, 47, 71. 45, 47, 71. Yeesh, I better hurry up. Okay, any other questions? All right, there, done that question. Beep, beep, let's get going. Question 81. World War II era rocket launcher called the bazooka was open at both ends. On the basis of momentum considerations, how is firing a bazooka different from firing a cannon, which is a tube open at one end only? Oh, um, there's a thing about cannons. Did you know this thing about cannons? Whenever somebody draws a cannon, they draw it on wheels. There's usually like a wheel here. And then, you know, the fuse. Um, and one question you could ask is, why is there a wheel? It turns out the wheels were important for cannons because, for a couple reasons. One, this kind of hangs over a wall, you know, and so you don't want everybody to go in and futz around the front of it because they'll fall off the wall. So, you know, they'd often tilt up and stuff. But so the wheel would push it back, would allow you to push it back and give you access to it. But even if you there's like a really weird battlement thing. If you ever go to a place with like a cannon fortress, sometimes the cannons are on like a thing like this. It's like a little track. And the deal is that as the cannon launched the cannonball, the cannonball indeed gets some momentum, and the cannon ends up with the opposite of momentum, essentially because the system is just cannon and yeah, I guess the air inside it, air. This ends up with a big minus P, which pushes the cannon back. And so the cannon will roll back, and then you can roll it back in place. So watch on your fun naval movies, pirate ships, the cannons are always on wheels. It's not just to give them access to it, but as you fire the cannon rocks back and forth. And the reason for it is because if you put it on a mount, it would break. It wouldn't be as mobile. Also, you can use the wheels to steer it left and right. Okay, so compare that to a bazooka. You watch a World War II movie. Bazookas are shaped kind of like... Oh, that's a bad drawing. Bazookas are shaped kind of like... that. And the idea is you shoot a bullet out of the front. Delta P. You shoot a shell out the front, and you hold on here. So you've got your gun and, you know, your army hat. I guess you're on the other side of it. You can't see the person because they're behind the bazooka. Hey, look, Ebenezer Scrooge is firing a bazooka. So, in this case, because the cannon is U-shaped at the back, because it's closed, the system here, the relevant system here is the cannon plus all this air. And all this air has nowhere to go as it shoots the cannonball forward, and so it gets deposited into the cannon body, which then moves backwards. In the bazooka, because it has an open back, the air isn't really attached to the bazooka, and so the air can move backwards. And so if it's just the bazooka, okay, so the air plus the bazooka system gets a big minus P impulse. But because the air isn't attached to the bazooka, most of the momentum is deposited in the air, and the bazooka doesn't pick up very much impulse. Anyway, that's fun, right? Blowing stuff up. Maybe you enjoy that. Maybe you enjoy shooting ghosts with bazookas. I don't know. Scrooge. My chains were forged in life from gold. They're much nicer than your chains, Scrooge. All right. Next question. Which one was that? 81. Okay, question 82. In a football game, a 95 kilogram player carrying the ball can run the 50-meter dash in 5.5 seconds. That's pretty fast. 2 opponents are available to stop him with a head-on tackle. 1 opponent has inertia 110 kilograms, and it can run a certain speed, while the other has inertia of 90 kilograms with another speed. Which has a better stance of stopping the 95 kilogram player, and why? Is there any suggested practice for the midterms? I don't know. These questions are good. All right. So there's a conversation on the chat, instant chat. My name, Jeff, says, is there any suggested practice for the midterms? And Sanchit Sharma says, I don't think so. There's practice tests. And the first person says, I have too many questions and too little time. And the other person says, if there is one, please link to it. Okay, so long and the short of it is you can do these questions. You can go into Mastering Physics and try the questions in there. The assignment, quote unquote, on Mastering Physics isn't for marks. It's there to give you practice on this material and feedback before the test happens. So if you want to do some inertia and momentum question practice, that's a good place. The practice exams are good. You can go through the other videos that I've made for this class and go through the previous questions there. Those are good questions. There's essentially lots and lots and lots of questions I've made available to you. I don't want to make a list of questions and give that on top of it, because if I also make a list on top of all the other material I'll give you, everybody's just going to bug me for answers to the question on the list. Just do the work I've given you already. Go to previous pages. Go to previous pages on the YouTube site. Other videos I've made for this specific class. Look up those questions, try them, and then if you have any questions about their answers, you can watch the videos, and I go through the answers in those, including this one. Alternatively, if you want good practice, you can try the practice tests. You can look through, do your Mastering Physics questions over again. So yeah, that's what there is. Just make a note as you do them what kind of notes you'll need for your question sheet. I mean your equation sheet. All right. So one question here, to do it, the idea is that you got one person and they're running with the football. Hello, I've got a football and I am running. And they can go real fast. And I want to know how much momentum they have. And so if I know what their velocity is, their fastest speed, that's given in terms of these 50-meter dashes. That's 9.1 meters per second. And so he's got a momentum this times 95. Okay, and then there are 2 other people who are running in the opposite direction. One of them has a 50 meter in 6.6. That's 7.5. 7.6 meters per second. And their inertia in it is 110 kilograms. So their momentum is, their maximum momentum is and the other one is littler but faster. They go 50 meters in 5.1 seconds. So 9.8 meters per second. Wow, if they ran straight up a wall, they could go a whole meter before falling down. And so their maximum momentum is 90. 882 kilogram meters per second. So the question is, who is best likely to run into this guy and cancel all his momentum? Is it the really fast person, or is it the really heavy person? And the answer is, well, it depends on the numbers. If the heavy person can go fast enough, then it's the heavy person. If the light person can go super fast, then it's the light person. And sure enough, the light person can go quite fast and has enough maximum momentum to cancel out this person's momentum. On top, the lighter person, whose in mass is only 90 kilograms, the lighter person has really bony shoulders and elbows and knees. And so when they run into this person, they can really stab him up good with his knees. Okay, so let's move on to page 183, if there aren't any questions about this particular material. Boop, 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 boop. So there were two questions on 183. There's questions 60 and 63. So object A, at rest on a low friction table, is struck a glancing blow by object B. Show that if the collision is elastic and the two objects have equal inertias, the angle between the final direction of motion of the two objects is 90 degrees. You guys don't know what elastic collisions are yet. We mentioned them at the end of last class, but I haven't gotten into it too much. So you might not know exactly what I'm doing here, but momentum is conserved. And also the kinetic energy is conserved. That's what an elastic collision means. So, the initial velocity, you know what? I am going to imagine that I'm going to rotate my axes so that B comes in and hits A, and B is moving straight to the left. I'm allowed to do this, to be honest. Hold on, let me explain. This is a physics thing. A is here. B is going to come in and hit A with some velocity. And then afterwards, they're just going to go whichever direction they go. In this case, VB initial has two components, VBX I hat, VBY J hat, right? This actually makes things, I mean, this is pretty complicated. So one of the things we can do, though, is we're free to choose our I hat and J hat coordinates. And so we can choose I hat to be in the direction of that. And that means that when we set the problem up, we can choose coordinates so that VBY is equal to 0. It's a choice we can make as we're setting up the proof. So let's just imagine a horizontal one like that. B's here, A's over here. They're not going to hit necessarily straight on. So VB initial is going to be, I'll call it just V I hat. Okay. And after, they go in different directions. This one goes in that direction. This other one goes in that direction. Okay. I don't know much about these directions. So, I know momentum is conserved. So the initial momentum in total, the initial momentum in the x direction, the initial momentum in the y direction, the initial momentum in the y direction 0, and that means that V y a V y b. That means that these two velocities, their momentums have to cancel out. So a times ma plus vyb and b is equal to 0. Their momentum in the x direction is just going to be mb times that v. So I can get these two vx vxa vxb. vxa times ma plus vxb times mb is equal to mbv. Okay. So conservation of momentum gives me these two equations. There's also the conservation of kinetic energy, which is 1/2 mbv squared. That's going to be 1/2 ma vxa squared plus vxb squared plus 1/2 mb vxb squared plus vxa squared. So the conservation of energy says these two terms must be equal. And then what we do is we okay, well, how would we even tell if these were 90 degrees to each other? Let's think about this. If they were 90 degrees, then this angle and this angle would add up to 90 degrees, which means that this angle is the same as that, and this angle is the same as that. Which tells you, okay, let's call one of these theta. If this one was theta, then this one would be theta. Tan theta is equal to VAY over V. Ooh, I got them backwards. VYA VXA. And on this diagram, tan theta is equal to VXB over VXA. So if they're at 90 degrees, these two ratios are the same. We're trying to prove that VYA over VXA is equal to VXB over VXA. Should be a B. VXB, VYB. Everything about that was wrong. All right. So let's I guess let's start doing algebra. There's a nicer way to do this with vector inner products, but you guys don't know how to take vector inner products. So, like dot products. So we just have to kind of work on through it. Okay. So let's start by solving this guy. MA is equal to VY B minus VYA MB. So these equations become plus VXB all right, and there's an MB term here. MB V squared 1/2 minus VYB over VYA times MB VXA all squared plus VXB all squared plus 1/2 MB VXB all squared plus VXA all squared. All right, so I took this equation, rearranged it, and did a substitution. The substitution is nicer than it looks because every term in this expression and this expression is multiplied by MB, so I can factor out the MB. The nice thing about this computer, this program, is it lets me factor out in this way. Nice. I can also factor out the 1/2 now that I see it. Okay. So now I guess I'll solve this equation for V, or rather I'll take this equation for V and I'll substitute it in here. So VXA times minus VYB over VYA plus VXB all squared is equal to minus VYB over VYA squared plus VXB all squared plus VXA all squared. You know, when I looked at this question on the list of questions, I was like, hey, this looks like a good question. I didn't read it very carefully. This is a very famous result from elastic collisions. After an elastic collision, the products always come out 90 degrees to each other. But I didn't read it very carefully, and now I have to do it according to the oath of the physics instructor. Plus 2VXA times minus VYB over VYA times VXB plus VXB all squared is equal to minus VYB over VYA. Whoa, what's going on? VXA all squared plus VXB all squared plus VXB all squared plus VXA squared. What? Is that even right? XB. What am I doing here? This is supposed to, oh god, look at this mistake. This is supposed to be YA squared. And this is YB all squared. That's the problem with doing algebra on autopilot. So that one's wrong and that one's wrong. I guess I'll correct them in a different color. This is supposed to be YA and this is supposed to be YB all squared. Okay. Look at this mess. Is there anything I can cancel? Copy. Paste. Sweet. Get to delete this one. Alright, if I didn't make a mistake, I think this one and this one cancel. And then VYB. And then what? Do I just have to multiply this out? Oh god. Okay, I'm gonna do a trick. I don't like this denominator and the fact it's squared, so I'm gonna multiply this by VYA, VYA. And I'm gonna multiply this by VYA and VYA. I'm going to multiply this one by VYA, VYA, all squared. And then I can cancel all the VYAs out, and you get VXA all squared times VYB all squared minus 2 VXA, VXB, VYA, VYB, and that's equal to minus VYB, VYA, VXA all squared minus VYB, VYA, VYA all squared plus VYB squared, VYA squared. And now I think I probably have to reorganize stuff. There's probably some factoring here. VXA. This one has VXA squared. These ones have VYA squared. So maybe I'll bring these over to the right hand side. VXA all squared, VYB all squared plus VYB, VYA, VXA all squared minus 2 VXA, VXB, VYA, VYB is equal to VYA all squared, VYB squared minus VYB, VYA. Oh, geez. What now? Ah. Boo. Oh, video output low. Oh, shoot. Did I even... how long has the thing been going on? I think we're almost good for the time being. Okay, you know what? You're not learning anything. So I'm gonna give up on this question. You just keep reorganizing these things. Oh, you know what you could have done instead? Oh, jeez. You could have redone these using VXA is equal to, I don't know, U cosine of theta. And then Vya is equal to U sine of theta. And Vxb is equal to W cosine theta. Vyb is equal to W sine theta. And then done it like that. That'd probably work better. Jeez. The thing here is, the thing you need to understand as you do this is that I really like playing around with equations. So I'm tempted to just finish the question because I think I'm onto something. I think you just have to keep rearranging stuff and then add some terms to both sides, and then you can divide stuff out by both sides, and then Bob's your uncle. But nobody's learning anything. I mean, you guys don't learn anything watching me do this algebra. So I'll leave it to you to finish this. My temptation is to finish it, but you guys don't learn anything. So here, give me a second to reset my thingy, and then I'll do those. Finish the other questions. Everybody study for the midterm. Nobody wants to watch me do algebra. Okay, which question was that? 63? Oh no, this is 63. Oh, this one's fun. Okay, so 63 is also a question that kind of involves stuff that we haven't talked about. It involves potential energies. So part B involves potential energies, and you don't know how to do it. But we can do the first part. It's pretty fun. So the deal is you got two blocks, 1 and 2, and they're sliding with this velocity, 2.9 meters per second. And then the spring expands, boing, and this one goes off this way, 3.5 meters per second at an angle of 34 degrees. And one comes off, and it's doing its own thing. Okay, so the total inertia here is 3.4 kilograms. And this one is 2 kilograms. And this one's 1.4 kilograms. And that's all they give you. So we want to know what the velocity vector, the final velocity vector is. And we're going to use conservation of momentum to do it. So the total momentum initially is equal to 3.4, the mass, times the velocity, 2.9 meters per second I hat. So 3.4 times 2.9, that's 9.86 meters per second I hat. So the deal is that this is an isolated situation. These blocks, as they're described, they're not interacting with anything in the outside world. So the total momentum of the system is still going to be 9.86. Only it's going to be broken up into block 1 and block 2. Each of these has I hat and J hat coordinates, which we can. All right, am I back? I think I'm back. Hello, I'm back. So there is. While I was away, it occurred to me this really elegant solution to the question of momentum and velocity from the previous example. You know that question I did above where your B velocity was coming in, and 1/2 mvb squared is the kinetic energy, and the momentum is mvb j hat. And then after the collision, they're going off in different directions. Well, it occurred to me that each of these has a momentum, right? I'll draw it in green. PA, that momentum, and PB, that momentum, and because of a conservation of momentum, the vertical components of these have to cancel out, right? And so if we added them together, PA and PB, your vector diagram would look like this: PA plus PB, and this is your original PB initial, straight horizontal, right? So this is equal to mvb. Now, here's the fun part. We wanted to say that these velocities were at right angles to each other, and if that's the case, then this must be a right angle triangle. And if this is a right angle triangle, then it means these sides are the sides, and this guy is the hypotenuse, right? So how long are each of these sides? This side is going to be, I want the length squared, PB squared. That's MB squared times VX B final squared plus VY B final squared. And then the hypotenuse, the length of this side, oh, come on, PA, that length squared will be MA all squared VXA final all squared plus VY a final all squared. And the length of this hypotenuse is MB squared VB initial squared. Okay, so here's the fun part. Wait, hold on. Okay, so this question says, if the objects have same inertia, MA is equal to MB. Okay, so here's the thing. This expression is 2 times the kinetic energy of A times MA. This expression here is 2 times the kinetic energy of B times MB. And this expression here is 2 times the kinetic energy of B initially times MB. And if energy is conserved, then KEB initial is going to equal to KEA plus KEB, as I've defined them up here, right? Multiply all of them by 2. multiply them by MA or MB, because they're the same number. 2MA KEA plus 2MB KEB. And then this is PBI squared PA all squared PB all squared. And what we've just showed is that this triangle satisfies the Pythagorean theorem, and therefore it must be a right angle. That's fun, right? I figured that out while I was rebooting the stream. So it just goes to show, sometimes it pays to reboot the stream. Man, this stream is going slow. It was going gangbusters a couple hours ago, but now it's super slow, even though I've rebooted everything. Oh well, I guess let's do these questions. So page 45, question 43. Dang, man. It's all buffery. I wonder why. It's got to be internet. I haven't changed any of the settings on my end, and it was pretty consistent for about an hour. I rebooted this guy recently. Yeah, okay. So I don't know. I don't know why it's so crummy right now. Let's just do these questions, and hopefully posterity will remember them. 45 question 43. Two cars are moving at 97 kilometers an hour, one behind the other on a real road. A deer jumps in front of the led car, and his driver slams on brakes and stops. What minimum initial distance between the rear lead of the car and the front of the second car is required if the second car is to stop before hitting the lead car? Assumes the acceleration for both. I did this question already. I did it already in one of the other feeds. Hold on. YouTube. Google our site. I've done this question. I did it like last week. Oh, maybe everything's crunchy because my internet connection's so slow. Dang. It's chugging along right slow. Beep, boop, bong, bong, bong. Dong, dong. Dang, I'm going to reboot my internet connection. Alright, that means I'll reboot the stream.